To lead our next session, I'm very pleased to introduce you to Kerry Brenner. In 2021, Kerry moved to Australia after 9 years at the UK Research and Innovation's Central Laser Facility. She's now the Director of the Australian Nuclear Science and Technology Organisation Centre for Accelerator Science. And a little extra tip here for you. This might be obvious, to be honest, but my guide is that if I applaud somebody and my hands hurt a bit afterwards, I'm kind of in the right. If they're bleeding, it's gone too far. But if they're hurting, you're in the right zone. Please put your hands together slightly painfully for Kerry Brenner.
Thank you. It's great to be here. It's my first ICRI, and it's great to be in the room with lots of people who we all share the same challenges, and we're all inspired by similar goals. 10 years ago, I invited an artist into one of the experiments that we were leading in the UK using a petawatt laser to understand high energy density plasma physics to explore novel accelerator mechanisms. It seemed at the time a bit of a risky, kind of open thing to do, but it was exciting, and we found an artist called Alistair McClymont to come on he had that open mind, to come on board through a residency, an artist residency called Beam Time. There was no expectation for the time he spent with us. He spent 5 weeks with us. Just come in, have a conversation, meet the scientific team, find out what we do, observe, learn, ask questions. What came out of that process really has inspired me and transformed my thoughts about what research infrastructure and science is in general. He saw a lot of parallels in the scientific method and the artistic method. He noticed that we were all asking big questions about the world around us, and that we were testing those ideas and questions through methods. We were interpreting the world around us, and we were then presenting our results afterwards. And so for me, it was a really inspiring process of understanding that science and art are actually extremely closely aligned in terms of asking the big questions about the world around us and then being able to describe that and to the world to support us as people on this planet. We're here in the hope and wonder theme. That's why I've started off talking about science and art already, about how we use research infrastructure to ask those big questions. And then the role of research infrastructure in setting up the environment where creativity and ideas can thrive. It's about creating the environment where people can come together, can test their ideas, they can challenge them, they can fail and fail fast, and then they can refine those ideas and come to some conclusions and give back in terms of scientific discovery, in terms of exploration. And that exploration can be about asking about where the universe came from and the big questions about where we are in the universe and the time that's gone before us. Or it can be asking about discovery and exploration that's going to support, as we've just heard, critical and urgent challenges of our lifetime that are here and happening right now. Creating the ideas, the creativity, the imagination that is going to solve those big problems, but also lead to a better world that we leave behind us, is where science has a big role to play, and research infrastructure is at the heart of enabling that process, that pure process of exploration and discovery to happen. Today, I'll be joined in this session with three wonderful leaders in global research infrastructure that all have one thing in common, that they're using particles and light to ask those big questions that are around us in the world. So I've asked the panel to join me now on stage. We're going to start with a brief introduction from everyone to give an opportunity to introduce to you who they are and the organizations they come from. And then we'll have an opportunity to ask a few questions, and then I will keep a very close eye on time so that we can also open up to the floor as well if you have any questions of your own. All right, so we're going to start off with Professor Rafał Dunin-Brogowski, who's the co-director of the Ernst Ruska Center for Microscopy and Spectroscopy with Electrons. He's also the spokesperson of the European Distributed Research Infrastructure for Advanced Electron Microscopy, otherwise known as eDREAM, a not-for-profit initiative formed to promote cooperation between European-level advanced electron microscopy infrastructure providers, collaborative research, and transnational user programs.
Great, thank you very much, Kerry. It's my second ICRI meeting, and it's a great pleasure to be here. The atmosphere is wonderful, and the discussions are also very productive. So we're dealing now with analytical research infrastructures, and my particular area is electron microscopy, and specifically electron microscopy for material science. And it's particularly appropriate that we are in Australia because electron microscopy is organized and managed and funded particularly well in Australia. I'm extremely envious, and I would recommend that it's supported even more strongly. I'd like to give you a European perspective now, and this is starting with how electron microscopy is evolving in Germany, where I work, in the Jülich Research Center, and then our moves towards creating a sustainable infrastructure in Europe, spanning different countries. And finally, I'd like to present a few open questions and a few opportunities for further development. I should also draw a distinction here between electron microscopy for material science in Europe and electron microscopy in biology, cryo-electron microscopy, which is much better organized with the Eurobioimaging and Instruct research infrastructures. This doesn't yet exist for material science, and this is one of the challenges that we are facing. So first of all, when we talk about electron microscopy, for those who are familiar with electron microscopy, we often think about atomic resolution imaging of materials. And this is an image of a very thin oxide film, just a few atomic layers thick. And on a modern electron microscope, the spatial resolution is much better than the spacing between individual atoms. It's about 3 times better than the spacing between individual atoms. And there's a model of the structure here. This is an oxide, yttrium aluminium perovskite. And in this particular orientation, some of the atoms are only just over 50 picometers apart, and the spatial resolution is somewhere between 40 and 50 picometers. That's about 20 times the wavelength of the electrons, which is being used to form the image. And we can magnify the image gratuitously, and we can look towards what an individual atom looks like, although the interpretation of images like this is not so straightforward. These images provide information about microstructure. You can also look at the composition and the chemical state of individual atoms, and even the bonding character between atoms, and even the spins of individual atoms or individual atomic columns. So electron microscopy has advanced enormously over the last 20-25 years. And if you look at a modern microscope, then it offers fast switching between imaging, diffraction, and spectroscopy. And there's been particular progress in resolution as a result of hardware developments, for example, aberration correction technology. And with some techniques, especially tachographic techniques, you can now go to a spatial resolution of below 20 picometers, just about 10 times the electron wavelength. This gives you much better precision in the measurements of the properties of materials on the atomic scale and in structure property relationships. Also, you can look at chemical reactions taking place in real time, and you can look at very fast switching processes. But one point I'd like to emphasize is that we currently regard electron microscopy as a laboratory scale technique, and rather than a large infrastructure. This is partly because the microscopes that are used are provided by commercial manufacturers. They're provided as almost black boxes with very little information provided to the owners or the users. And this is despite the fact that most developments in technology start off from academic research laboratories. So one thing we would like to do is to take electron microscopy to the next level, to develop instruments beyond those that are made by commercial manufacturers. And we would like to encourage co-development in a better way between academic laboratories and manufacturers in the future. And this brings me to my perspective on what is happening in Germany, where I currently work, where we're trying to take electron microscopy to the next level in terms of instrumentation. So I work in the Ernst Ruska Center in the Jülich Research Center near Cologne and Aachen in Germany. And we were operating for 20 years as a national user facility with a focus on methodology and instrumentation development. And currently we operate 20 tools, 20 instruments in our building. And about 12 years ago, we started to ask the ministry how we can take electron microscopy to the next level. And following 3 years of discussions, we were invited to apply for the national roadmap for large infrastructure in Germany as electron microscopy. And that application was successful. And in 2019, we, with the funding that we raised through being on the national roadmap, we ordered 5 next-generation electron microscopes, which are beyond what you can buy commercially from any manufacturer. And I won't go into the details of what the instruments will be able to do. They will be delivered over the coming 2 years. But we are talking not only about improving spatial resolution, but improving many other ways in which materials can be studied. And this includes going to extremely low temperatures, doing very complicated correlative characterization, looking at working quantum devices in situ, and so on. So in Germany, this is what we're doing, but Germany is in quite a unique position here, not only because electron microscopy is on the national roadmap, but because in many other countries there is not even the possibility to provide access to electron microscopes which are located in academic laboratories or research institutes. And this brings me to the European perspective. And in Europe, over the last 20 years or so, electron microscopy has been supported through 3 successive integrated infrastructure projects, each 4 years long. And they provided networking, transnational access, and joint research between 15 laboratories within Europe. These were projects which each had a finite lifetime. They achieved incredible success, but that funding stopped in 2023. And this brings us to the question of where we go next with funding access to electron microscopy laboratories as a distributed infrastructure in Europe. In anticipation of the funding ending, we created the eDream network, the European Distributed Research Infrastructure for Advanced Electron Microscopy. This does not inherently come with any funding. This is more to develop a longer-term strategy for how to develop electron microscopy for materials science in the future in Europe. It's made up of a subset of 8 of the former laboratories from the previous STEAM network, as it was called. And so far, it's managed to secure 4 European Commission projects. But again, this doesn't give us sustainable funding to support access to electron microscopy in all countries in Europe in the future. And this is one of the challenges that we're currently facing. Yesterday, we heard from the chair of the European Strategy Forum for Research Infrastructures, Professor Martinez, about a landscape analysis, the ESFRI landscape analysis 2024. And electron microscopy is fortunate to be mentioned in the landscape analysis in the form of the STEAM and eDream networks alongside synchrotron X-rays, free electron lasers, neutrons, ion beams, magnetic fields, and lasers. And one of the challenges, as I mentioned, is to make electron microscopy more sustainable in terms of funding for access. This is an ongoing discussion about how we should do this. But the other question that this figure brings to mind is how we ensure the best possible cooperation between different analytical techniques. At the moment, we have individual experiments which bridge between, for example, X-rays or neutrons and electrons, but we lack at the moment specific standards or workflows for interoperability in sample design, in sample cartridges, in metadata, in data handling between different techniques. And this is also one of the challenges which we need to address in the future. And this brings me to my concluding slide, where looking towards the future, we'd like to think about sustainability of access, joint research and networking, but also interoperability and cooperation between electron microscopy and other techniques. And that's my perspective to begin with. Thank you.
All right, next up I'll invite Dr. Nicole Alouche to the floor. She's the Managing Director of European XFEL and oversees more than 500 professionals from 60 countries, managing a 150 million euro budget. Nicole's background includes executive roles in German research institutes and as scientific advisor for the UN in Geneva. She has a strong scientific foundation as a molecular biologist, postdoc experience in the USA, and holds an MBA in science and research management. Nicole actively serves on various advisories and review boards, demonstrating her commitment to advancing scientific research and innovation.
Thank you. Good morning, everyone. I wanted to start with, from the bottom of my heart, thank you for the invitation and the opportunity to join ICRI in Australia, Brisbane. That's just fantastic, and this also in particular goes to the organizers here, and all the volunteers. You're such a warm, literally warm welcome, but also to very different aspects. I'm really enjoying the time here with all of you. Thanks for that. So fortunately, I can actually kind of skip my first slide, roughly, as many of the things which are written there already said. Carrie, thanks. So European XFEL is a very young facility. So we were built 2009 to 2017 with the funding of 1.5 billion euros. 60% of that funding were provided as in-kind contributions by our 12 shareholders. We are running the facility with 150 million euro spent by 750 staff members, roughly, and their main goal is to create an environment where excellent science can be conducted by the roughly 1,500 users we have per year. So in total, our staff is coming from 60 countries, and the users, since we started the ramp up of the facility and full operation in 2022, so the user community is also representing roughly 80 countries. So we are providing 9,000 hours of beam time with our experimental stations distributed to 100 experiments, which is one of the main goals at the moment, to stabilize that, because we are still considering ourselves in kind of a teenager age. We are finding out where we can become better, and also be a little bit of kind of a how to spell that diplomatically. We still provide many of improvements of organization and structures to also our shareholders, to show that we wanted to go into the harvesting phase of what we can produce to do the best science possible for the globe. So we were asked to also present some challenges today, which can be discussed. One of our challenge at European XFEL, based in Hamburg, Germany, by the way, is our composition of shareholders. As we are located in Germany, the biggest shareholder is Germany. The second biggest shareholder is Russia. And then the other European shareholders are having 1 to 3 percent of the shares of UPenn ICFAL. So we are running the facility considered as an international company under European and German law. And in our convention, it's clearly written that we are doing activities for peaceful ends only. However, the free electron laser is listed as dual-use technology, and the access is quite significantly restricted, which is a topic keeping us busy every day. So selling what we are doing and showing also that we contribute to solving societal challenges. We, of course, refer to the Sustainable Development Goals and can particularly do something in 4 areas besides fundamental science, which is the core of research infrastructures still, and this cannot be emphasized more, is my opinion. Beside that, coming to the 4 areas referring to the SDGs, we are looking into the environment and sustainability. Digitalization is a very important topic for us, where we can contribute with the experiments which can be conducted at UPenn ICFAL, looking into reducing data, looking into new storage capabilities. Climate and energy, so of course we are also looking into, that was just mentioned by Werner, how we can better understand photosynthesis, but I will also show a slide you might not like. So, and photovoltaic, sustainable resources, these are all topics which are driving us and our users. Last but not least, health is one of the topics where you can really do experiments on in a particular way. We can do molecular movies of molecules, of atoms, and understand processes to develop new treatments and diagnostic tools. So also presenting to the outside that we are quite close to what is a scientific trend and can change the future. We like to use the argument that we work closely with the ones who have conferred to greatest benefit to humankind, to just quote Alfred Nobel, which I've never done before, I'm nervous, you know. So we have many partners, and in particular 3 Nobel Prize laureates working with us since a longer time, and also contributing to the technology which is used at UPenn ICFAL. So Donna Strickland, we are using her lasers, and she's also developing her lasers together with us, which are used in our experiments. Then Anne Lhuillier, just getting the Nobel Prize for attosecond science last year. She, until she got the Nobel Prize, she was a member of our scientific advisory committee and has really shaped the attosecond science area at UPenn ICFAL. Last but not least, the Nobel Prize for chemistry just this year went to David Barker, and he just got the first diffraction pattern of one of his de novo proteins with our technology at UPenn ICFAL. He's a regular user of our facility. So yesterday I was at a session where we talked about the size of research infrastructures and which size might be the best to still be agile and flexible to react to current trends. So this is what I wanted to show you on my next slide. So fusion energy is a new research area. We want to contribute to look into fundamental questions of this mind-blowing development we see everywhere. Of course, our shareholders are also quite interested in that. And I also agree that it might take longer than a decade, which is promised by some of the colleagues in the fusion bubble that we have a first plant. Nevertheless, I think that is also a topic we have to look into to create a sustainable future. And UPenn ICFAL is until now, with one experimental station, which is the high energy density station, the only facility who can really look into the details of the fusion under different conditions. Last but not least, our societal responsibility as research infrastructures. I wanted to mention that we have to show that we are much more than the pieces we are composed of. So taking care of our staff and community, preparing the young generation for their future, and also presenting to the society, to the public, what is the added value of research infrastructures as something which is which we have to do as research infrastructures to also kind of provide some arguments why we get this immense funding we are using. I've not gone into the technical details of UPenn ICFAL, but I would like to take the liberty to show you a short movie before I thank you. And this is on my next slide. I hope this is going now. Take 60 seconds to follow a short journey through UPenn ICFAL and its technology.
27,000 light flashes per second, and a brilliance that is 1 billion times higher than other conventional X-ray radiation sources. The X-ray flashes are so short that they can be used to film ultra-fast processes in the microcosm. The journey of the electrons begins in a so-called particle accelerator and ends here, 3.4 kilometers away in an experiment hall the size of a football field. During this journey, the electrons in the yellow superconducting modules are accelerated at minus 271 degrees Celsius. After 2 kilometers, in which the energy of the electrons continues to increase, the tunnel divides step by step into 5 more tunnels.
Here are the so-called undulator systems, 200-meter-long magnetic structures in which intense light flashes with laser properties are generated with the help of electrons.
Thanks to the extremely high peak brilliance, scientists can also examine very small samples, and the large number of 20,000 flashes per second mean that the experiments can be carried out faster than with other X-ray lasers. With the help of these extremely bright flashes, thousands of images are produced which scientists can use to calculate the 3-dimensional structures of molecules and particles. The research goes deep into the microcosm and the nanoworld. It opens up completely new dimensions and fascinating possibilities.
Thanks for your attention.
Next, we've got Dr. Jamie Schultz, who's the director of the Australian Centre for Neutron Scattering at ANSTO. Jamie is a prolific champion of using neutrons to solve complex research questions and industrial problems for Australian and international users. Over to you, Jamie.
Thanks, Kerry, and it's great to be here. So first of all, I'd just like to really introduce the ANSTO, which is Australia's Nuclear Science and Technology Organisation. We are an organisation that has been... so we're a leader in nuclear science and technology. We've been operating safely for over 70 years, and over that period of time, we've operated 3 nuclear reactors, with 1 reactor completely being decommissioned and returned to a greenfield site. So we have that expertise in understanding the whole part of the nuclear fuel cycle. We've got over 1,350 dedicated employees, and of that, we have about 600 PhD scientists supporting the facilities, but also supporting the operations that we have across our site. And of that, we manage $1.5 billion worth of research infrastructure. This is a significant investment for Australia, which of course we make available to international researchers as well. So at the heart of what we do is the Opal Research Reactor. It is not simply just a research tool, it is actually a medicine factory as well. So every week from that reactor, it produces over 1,200 patient doses across Australia every week. So having impact in real people's lives. Also doing silicon transmutation, so we're taking silicon and turning it to semiconductor. We put 90 tons worth of silicon through the reactor last year. That is over half the supply of the world's silicon for high-end applications. So it is not just simply about research. And of course, my area, the Australian Centre for Neutron Scattering, we take neutrons from the reactor as well, and we steal some of them. We steal them, and we actually do some great science with them, and I'll talk a little bit more about that as we go forward. We have the Centre for Accelerator Science, which is led by Kerry, where we're using ions to look into the past, but also to make materials for the future. We've got the Australian synchrotron down in Melbourne, which is a significant investment in Australia and supporting a significant amount of research. And the world-leading National Deuteration Facility. If you're not aware of this facility, its main purpose is to replace hydrogen with deuterium and many molecules which are used primarily in neutron scattering, but also now being used in health applications and other pharmaceuticals. And of course, we're underpinned by NCRIS. NCRIS is a fantastic initiative of the Australian government and supports us in delivering great services to the Australian researchers and industry, but also enables us to support international researchers as well. For those that don't know, the neutron scattering community in the world is really quite small. We're quite a small community. And you can see there's a number of facilities which are currently in operation. We've had a few that have shut down, and we've got a few that are having some challenges at the moment, and there's a couple that are coming up on the horizon. Within that community, we work quite strong. For example, if we're having a long shutdown in some parts of the world, we'll see migration of researchers from that part of the world to our facility. And for example, during the great tsunami and earthquake that happened in Japan, we transferred the user program of Japan over to our facility whilst they recovered their facilities. So we're really about partnerships and working together. So if you ever have the pleasure to come to ANSTO, and I will invite you to come to ANSTO at some point in time, you're more than welcome to come and have a tour of our great facilities. We have, this is the view of the neutron guide hall, looking back towards the reactor. So the reactor is at the back. We have neutron beams, tubes that come from the reactor and support the number of instruments that we have across our facility. This is the overall layout, but what I really wanted to highlight here in this picture is that you can see two logos. There's the logo of Helmholtz-Zentrum Berlin. So the Burr 2 reactor was shut down in 2017 in Germany, and they transferred and donated one of the instruments to us here at ANSTO. And we were able to then put that into the user program and continue that relationship of Australia and Germany over that period. We've also have an instrument which has been constructed by the National Science Council of Taiwan, which is an $8.5 million investment into research infrastructure at ANSTO. So you can see here that we have those international partnerships, and they're critical in what we do. And we'll see how we continue to grow those into the future. Research is just not done in Australia by Australians. It is done in partnership with international researchers, but also researchers coming to our facility to use us as well. And you can see there that we have quite a significant demand or usage across our facility over the last 4 years, and it covers pretty well every country around the world. We'll continue to maintain those relationships, but of course, in this challenged world, it is becoming harder. And that's one of the things we're trying to grapple with at the moment, looking forward in the future. And then, of course, this doesn't happen just by simple machinery, stainless steel, lead shielding, and electronics. It's the people that are behind this. So this is my team at the Australian Centre for Neutron Scattering. We have 23 countries of origin there. So we have quite a diverse team, quite a small team, but we work well together. And we try and make sure that we have a workplace that is about asking questions, safety is foremost, but also delivering great science and great user service. Thank you very much.
Have I got this on? Yes. All right. Great. Thank you. So now we've got some time that I'll just ask a few questions to the panel, and then if you've got any of your own, please have a think, and then we'll send some roaming people around to ask questions right at the end. So, Jamie, you were just touching on there about global collaboration and the importance of having an innovative mindset in order to achieve success in large-scale research infrastructure. So can you just speak to some recent examples of significant scientific achievements or discoveries made possible by those international collaborations within your community, and how do you envision these partnerships evolving to address future global challenges?
Thank you. It's really hard to choose your best child. So there is many great science stories that come out of ANSTO. The one I'm going to talk about is barocaloric materials, if you may have not heard about these materials. So these are new materials that, when they're compressed, they give out heat and have the potential to be used in refrigeration. So removing the need to use fluorocarbons. So from an environmental perspective, it's a really great opportunity. And so this partnership, which was actually led by China, who manufactured the samples, but in collaboration with JPark, a neutron facility in Japan, and ANSTO, we looked at trying to understand the mechanism by which these materials work. And so using inelastic neutron scattering, we determined that it's actually an entropy-driven process. So when you compress it, you're changing from being a high entropy to a lower entropy, gives out energy, and therefore cools the device down. So we're looking now at how these can be used in the future. For example, in microelectronics, there's a great opportunity there where you want to have great heating consistency, where you can actually compress it in some way and then also make it cooler.
Beautiful. It's the benefits of curiosity right at the heart of that. Wonderful. Nicole, from the XFEL community.
Yes, thanks for the great question. And of course, collaboration is quite close to the heart of a research infrastructure and a user facility. I just wanted to give you two examples which are great to just kind of underpin why this collaboration at a research infrastructure is so important. It's everywhere important, but in particular because we can provide certain, let's say, equipment facilities. So during COVID, there was a problem that people cannot travel and also the science had to be conducted to find out how we can develop a vaccine or a treatment against COVID. So what happened at European ICFAL, we closed the laser facility, so the laser was not operating, but we kept open the excellently equipped laboratories, and we've given the opportunity to work on the samples with the companies developing the vaccine. So we also managed that some of their scientists traveled to European ICFAL. They used our wet labs, let's put it that way, to prepare their samples, and as soon as we started operation of the laser again, they also used the samples to be looked at the European X-ray laser, or using the laser technology. So we could contribute to the development of the vaccine at the end, and this is something which also is adding some kind of belonging and ownership to all the people working at European X-ray. That made something for them, and there was also facilitating the digitalization of the whole lab, as you can imagine, because the whole community was working from everywhere. They wanted to see what's happening, so that's why we transferred the whole laboratory into a kind of a studio, TV studio.
I love this. It's the power of purpose, right?
Yeah,
Bringing people together under purpose. Rafael, for the electron microscopy folks.
Well, I'm not sure if this is working.
It is.
So I would say that everything is done in cooperation. In our case, we make sure that every one of our scientists does not work doing service operations, but in cooperation with external users. So the examples could range from studying biomedical implants, where there's correlative characterization between X-ray techniques and electron microscopy to study degradation processes around implants, or looking at battery or catalytic materials at different length scales. But I would also say that the cooperation between different research infrastructures also includes development of techniques, for example, development of new detector technologies or data management processes, or even approaches for remote operation of instruments. These are often developed in cooperation between people working on different techniques, and this emphasizes how people working on different analytical infrastructures benefit from working together, because often the techniques and the instrumentation bridge between different techniques.
Wonderful. Yes, it's kind of constantly striving for that next big thing, and getting people to constantly be in that ideation mode, constantly improving. So talking about emerging technologies, with rapid advances in emerging technology, such as AI, there's the AI bingo card if anyone's counting. I think every session we've mentioned it so far, but also things like automation and other ways of looking at detectors or remote working and so on. How are you adapting to integrate these innovations into operations, and what policy changes are critical to enable the successful implementation? So, Rafael, if you just wanted to carry on that conversation.
Maybe I would say that AI means different things to different people, and you could think of image analysis, you could think of instrument control, you could think of automating the workflows for designing and carrying out more complicated experiments. But I also mentioned remote operation, remote access, and this is enabled by AI control of instruments. And remote operation also has another implication, because yesterday we heard about reduced environmental impact of research infrastructures, and the more you can control them remotely, carry out experiments remotely, the less people need to travel to use instruments elsewhere. So I think AI can be regarded from many different directions.
Yeah, well, truly global. That means really open doors wherever you are in the world. Nicole, what's the XFEL perspective?
Yes, so well, let me start with the AI perspective, and adding to what was said. Of course, there are different directions how you can address AI. So we are using our AI in particular to reduce the data amount we are producing. So that's quite an important aspect for us at European XFEL. One experiment can produce up to, one experiment is running for 5 days. Told you 100 experiments we have per year roughly, and one experiment can produce up to 16 petabytes of data. So that's immense. And besides the aspect of sustainability and storing all these data, we also want to provide these data as soon as possible to the scientific community to let them write their papers and publish their experimental data. So that's why we are looking into kind of applications which can also be used by other facilities to clean the data, to store the data, to pre-select the good data and distinguish from the bad data. So this is something where we are putting some resources in and trying to find the best people to do that, because there's also a big demand on people who can work on AI applications. So that's a challenge for us as well. That's one of the aspects. The other aspect is really to train your people to use AI. So I was on a conference where I heard a nice quote, which is, AI will not replace you, but AI might replace you if you don't know how to use AI. And I think that's quite true. And I think we have to train our people how to use that. We have to increase the awareness about the openness of AI, what you put in. So that means we need policies, we need guidelines and regulations, how free AI tools are allowed to be used at our facilities, and that also is asking for a joint approach, maybe of research infrastructures, because I have heard that some infrastructures are developing their own AI solutions, and if we can have these kind of protected solutions to be shared within our community, that would create a big added value for all of us, I think.
Yes, so adapting to what's coming, whether you're on board or not, but I think, making sure that you're ready for that. Jamie, is there anything you'd like to add to that?
I think from neutron scattering, we're quite in the infancy stage of adopting AI, but one of the big things for us is thinking about how we manage, when we put data into AI, it gets shared, okay? And that's one of the challenges when you start to think about export controls and other aspects. So having your local level AI clients or tools, but also maybe sharing them within a trusted network. So that's mostly one way that you could go. The other challenge we find is remote access. Everyone would love remote access, but for a user facility like a neutron scattering facility, we're really dependent upon the users to come and do the experiments. We don't have enough staff to do the experiments for them. And typically we don't know how their samples work, so they need to be able to load them, prepare them themselves. So that whole aspect of it is really important to ensure that you still maintain user facilities, but there's also that training aspect, because relationships you build through your PhD doing experiments at large-scale facilities will go with you for the rest of your life, and I think that's really important for developing those relationships.
Wonderful. Just before we close out the session, I just wanted to throw it out to the floor now. If there's any questions, there's one hand just shot up there, and there's another one at the back. So in case we have time for a couple of questions before the break.
Thank you for a very nice session. So even XFEL is already, it's sort of a light source, but it's really a particle accelerator, right? Before you get the light source. And so there are a lot of connections, even in the current state-of-the-art infrastructure, and certainly the next generation, between the light source community, particle acceleration community, right, optics community. And then to design those, to design and implement those, you need the new materials often. Materials is often a challenge, and some plasma physics, which is my expertise. So can you comment on connections between your communities of people building new infrastructures or the users helping you to build new infrastructures?
Yeah, thanks for the question. Of course, so hearing your question, for me, the most important aspect is how we can look into the community and create joint technological advances. So if we look into detectors, into undulators, into accelerators, at the moment, the whole community is, from my perspective, a bit of fragmented. Of course, it's also driven by competition, and it's also a bit of the balance between competition and working for the community. I have a very clear opinion here. I think we can all create an added value for the whole community if we would work closer together, and in particular, if we would kind of inspire also the commercial branch of developments for undulators, accelerators, new detectors, whatever, that would give us the advantage to have a better supply chain, to have more partners we can also commercially work with. And this is something which is not that emphasized as it could be looking into the global situation.
All right, wonderful, thank you. There's one more question before we close out.
Yes, hello, thank you. My name is Adam McLeod, AquaWatch Program Manager from CSIRO. We heard a lot about collaboration and cooperation, and scientists and engineers love to solve problems and fix problems, and in the case of scientists, produce papers. But zooming out one level, there's valuable IP that's produced from these facilities and from research infrastructure more generally. So where there's projects or delivery of this research infrastructure that produces the IP, and it's done in a collaborative way with multiple countries being involved or multiple organisations, how do you manage the sharing of that IP, the outcomes of the delivery of the infrastructure or the science that comes from it?
It's a great crunchy one. Who'd like to take that first?
Okay, from an electron microscopy perspective, what we do is we set up joint development projects with companies that we want to work with, and any IP that's developed is either shared, or if it's IP owned by us, we license it back to the companies afterwards, and then they sell it, and then we receive a royalty afterwards when they sell it to future commercial customers, and that's how we cover some of the operating costs of our facility. So from our perspective, we discussed that from the beginning, and we set it up as joint development projects.
We follow a very similar process as well.
Same for us. I think what is important is that, of course, you are aware when you come as a user that what is the background of the IP and how this is used. And transparent communication is quite important here, because sometimes we have the impression that this is not clear for the scientists, that maybe the rule is different for sharing IP when you do your experiment as a research, at a research infrastructure than compared to your home institution. And this is something which could be added to the maybe preparation of the users.
All right, thank you for those couple of questions and for this session. So just to kind of wrap up, there are a few areas that naturally that it's common to all of us, and there's kind of one more question that I guess I pose to all of you to talk in the coffee break and also the networking events that we have space for in the next couple of days, is as our scientific landscape evolves, think about what strategies that we need to employ locally in our organizations, but together in partnership and globally to make sure that we can sustain funding and money so that we can attract top talent that have the best ideas, and so that we can maintain our relevance as research infrastructure in the face of competing priorities and resource constraints now in the next 10, 20, and 50 years to come. So with that, I'll close the session. Thank you very much to my panel members and to yourself for being here. Thank you.